Hi guys, I hope you're doing well. I'm in the process of trying to get this video going for you so that you can have videos to accompany the notes that I post on the days that we don't have live meetings. My plan is to have one live meeting every week for your class. So since we officially meet Monday, Wednesdays, and Fridays, you will have videos with assigned notes and homework on Mondays and Wednesdays from me, unless it's a test day like it was yesterday. Like it was on Monday, or we will have a live meeting, which we will only do on Fridays for our class. Now, I would like to start section 7.1 with you, and I'm going to try and screen share here the notes so that as I talk through them, you can see them. I've also attached the link to this assignment on Blackboard so that you can download these notes yourself and print them out if you wish, or you can just take notes along while you listen to the video, as you might normally do if we were in class and I was showing you these notes on the screen and you were taking notes on your own. Whichever method is the most useful to you as well as the most comfortable. Again, if you've got any questions, feel free to always email me. I try to answer them as best as I can, but I would urge you to please try to read through the messages and things that I post on Blackboard. There's a lot of times some of the questions you're asking me, I kind of already answered on those posts. But always feel free to ask if you're in doubt. I don't want you to struggle during this time. It's hard enough as things are, isn't it? All right, let's get to class. So here is my screen. And let me make that a little bigger so you can see that well. Okay, so we are starting chapter 7 and we are starting our discussion on decimals, which is very closely related to fractions. So it kind of makes sense that this is our next step after we finished our fraction chapter right before we went on spring break. And that's the test that you took on Monday. So as you can see here, decimals are defined as used to represent fractions in a base 10 place value notation. So basically the decimal notation that we're so accustomed to, or that your students might be accustomed to when you're teaching them in the classroom, is really just a base 10 way of representing fractions instead of just using the fraction notation that we saw in chapter 6. There's a very nice figure that you can look at on page 253 of your textbook, figure 7.1, and it looks kind of like this. I tried to reproduce it here myself for you, basically just so that you could see the place value chart, something that you're probably very familiar with. As you can see on the left-hand side of the decimal point, that's this little black dot right here, is the place values that we're accustomed to: ones, tens, hundreds, thousands, and so on into infinity. On the right-hand side of our decimal point, we have the place values for fractional values using base 10. We have tenths, hundredths, thousandths, and then it goes out 10 thousandths, and then it would be millions, and then 10 millions, and then it would be the next denomination down. So we always do it on base 10. And if you look here at example number 2, if we were to take this decimal point right here and place it on this place value chart, we would see that the whole numbers, as I just mentioned, are on the left-hand side, and the fractional portion is on the right-hand side. And when we read a decimal, we always read the point with the word and. So reading this from left to right, we would read this as 3,457 and 968 thousandths. We always attach the name of the place value of the very last digit on the right-hand side of the decimal that is not a 0. So the very last non-zero digit. As you can see, the 9 here would be in the tenths place on the right-hand side of the decimal. The 6 here would be in the hundredths place on the right-hand side of the decimal. And the 8 would then fall in the thousandths place on the right-hand side of the decimal. Hence, when we read it, we say that this portion is 968 thousandths. Note that we still read it as a number from left to right. We just attach, as I like to say, the last name of the place value of the last non-zero digit on the right of the decimal point. Now, There are some various ways that we can look at decimals, and one of the ways that we like to look at it is by using expanded form. Now, you may be very familiar with expanded form from our earlier discussions on place value, but officially expanded form is showing digits, that's why I've highlighted that part in yellow, with the place value that they represent as an addition expression. So for example, the same decimal that we were talking about here, if we were to write it in expanded form, we would take the digit 3 and show that it's being multiplied by the place value where it's in, which is the thousands place. Plus, we would take the digit 4, as you can see it's highlighted in yellow, times its place value, which is hundreds place, plus the 5, which is in the tens place, so times its place value, plus 7, and it's in the ones place, so times its place value. And similarly, you would continue doing the same for the fractional portion of this decimal, and you would show it multiplying by its place value. So the 9 is in the tenths place, so it's times 1/10. The 6 is in the hundredths place, so it's times 100. And the 8 is in the thousandths place, so it's times 1,000, even though that kind of fell off here on the document. Now, it is important, and when you're teaching this, it's important that you teach this well. It is important that you teach the word form of numbers, all numbers, but in our case, decimals, since that's what we're focusing on, because it is important that students know how to read these numbers correctly, and how to read them correctly is very much connected to knowing how to use the word form of that particular number. So here's how we read, and you'll notice that I have it in quotation marks, any kind of decimal, okay? So if we look at this example here, you will see we've got the decimal that we've been working with, right? And from the expanded form, we know that this is really the whole number, 3,457, and the fraction portion, which is 968 thousandths, okay? And I would make this little note for you here. You should know that that kind of looks like a mixed number, very much like what we saw in chapter 6. So you can see that there is a direct connection between decimals and fractions. And the way we read this, of course, is 3,457 and then I'm going to see if I can move this up for you. So, there we go. All right, let's see. There we go. And 968 thousandths. Okay, so it's very important that you know how to use the word and for the decimal point. Read the number from left to right, and then make sure that you put in that last name for where that last non-zero digit was on the right-hand side of the decimal point. Okay, so we've looked at word form, and we've also looked at expanded form. Let's look at what they call 100 square, okay? Those 100 square from those base 10 blocks that we looked at earlier in this course can be very useful in introducing the concept of decimals, because you've got a big square that is already divided into 100 pieces, which is base 10. So we look at the 100 square as our one whole. So 100 square would represent one whole number. Let's say you wanted to represent the decimal 3 and 5/10, you would have 3 whole 100 squares, and then you'd have 5/10, right? And the way we look at it is the 100 square is a whole, one whole. One whole column is a tenth, right? Because it contains 10 ones in it, but it's also 1/10 of the entire whole 100 square. So right here, this would be 1/10, as you can see here, labeled in fraction form or in decimal form. And then one little tiny square, which would be a 1 when we're using base 10 blocks, but here it would be 1 out of 100 squares contained in this 100 square, is 1/100th, as you can see here, written in fraction form or in decimal form as 1/100th. There are some really good examples for us to use practicing this concept of using the 100 square for representation of decimals. And you can see that in figure 7.2, which is on page 253. And I'm going to scroll down and show that to you because it's got a couple of problems that I think it would be nice for us to discuss. Okay, so here's figure 7.2 as you would see it in your textbook on page 253. So 100 square is one whole. As you can see here, they highlighted the 1/10 as I did in my illustration, and they highlighted the 100th. But here, for example, if I wanted to show 4/10, I would highlight 4 of the tenths in this 100 square. And if you were asked to write what is the decimal being represented by this image, you would say it's 0.4 or 4/10. Now let's say that I want to represent 7/100 out of this 100 square. Once again, I would highlight 7 of the individual little squares, which as you know represent 100. I would highlight 7 of them. And because it's not the full 10, I know that I'm talking about hundredths. I have 7 of them highlighted, so this is either 7/100 in decimal form, or here it is in number word form, 7/100. I hope that's helpful. If you need further explanation, there are some good videos that you can find on YouTube for Khan Academy, or you can always email me. I'd be more than happy to continue explaining it. Now, the final way that we can look at and think about decimals is by using our number line concept. Now, you know that from the beginning, we've been using this number line concept to help us discuss a lot of the different topics that we've talked about so far in this course. And it is still a useful tool. So you can see here that we would take a number line and divide it into one or more wholes. In this case, this is one whole moving in towards 2. I think it might be 2 wholes. And you would see that we would then take the distance between 0 and 1 and divide it into 10 equal parts, because remember, decimals are talking about fractions in base 10. And so therefore, this would be 2/10, and you could see that 0.25, right, would be between 2 and 3/10, and you can see it's right smack in the middle of that. That 0.5 or 1/2, or 5/10, which you know reduces to 1/2, right, would be right here at the halfway point between 0 and 1. And for example, you can see here that 0.695 is obviously way past 0.6, but not quite at 0.7. So it would live somewhere here on the number line. And we can even do quote unquote mixed numbers, as we talked about from chapter 6, because for example, here is 1. We are now past 1. So this would be 1.1, 1.2, 1.3, 1.4, and here we have 1.5, or halfway towards the next whole, which would be 2. So the number line can be also very useful to help us when we're trying to explain the concept of decimals. Now let's look at some practice and problems here, okay? If, for example, you were asked to take this fraction, 7/100, and turn it into a decimal, you would simply say, okay, 7/100, how do we write that as a decimal? As 0.7. If you really want to get technical, and when you're helping some of your young students, this might be helpful, you would tell them that the way we take any fraction that is written with a power of 10 denominator, which is what 100 is, you take the numerator, you write it down after the decimal point, and then the number of zeros tells you where, I'm sorry, let me try that again because I think I'm confusing you. Let me try that again. You take the numerator and write it down as a whole number. And as you know, all whole numbers, if we don't write anything after the decimal point, the decimal point lives right here, right? All the way over to the right of that whole number. Then the number of zeros tells you how many places you have to move it over. Okay, so you would have to move the decimal point over to 1 and 2. So the decimal point for 7/100 should be right here. This actually was intended to be 7/10, as you can see why I have made that error there, but I will fix it because that is definitely a mistake. This should be either the decimal point should be all the way over here where you see my cursor, or there should not be this extra 0 here. Let me see if I can use a whiteboard feature to better show you what I mean. Okay, let's do that. So what it should be is that this decimal should really be over here, okay? Because this is 7/100. And like I said, you would write down the whole number, which is 7. You would place the decimal point to the right of the whole number. And then you would count the number of zeros, 1, 2. So therefore I have to move it over 1, 2. So really, and let me see if I can change the color here. I can. Really, this decimal should be written, and I'm just going to draw an X through here, should be written as 0 point, and pardon my scribbles as I get used to this, 0, 7. Oh, wow, that's pretty terrible, but I think you can tell what I'm doing here. Okay? And I'll try to erase that. There we go. Let's try that again one more time. You know, this is a learning curve for all of us, isn't it? So let's try that again. It should be, no, I don't want the eraser anymore. Let's do that. Okay. So it should be 0. Oh, it's still not writing for me. Let's try that. Oh, wow. Apparently now I've just went and messed it up trying to show you here what I was doing. Let's try it one more time and see what we get here. Let's annotate. All righty. And see if it'll let me. So this should be 0. There we go. 0.07, which would be 7/100 as is written here for the answer. Okay, and then over here, if we look at here, and you know what, I'm kind of glad I made that mistake on the notes. It gave us the opportunity to discuss it, but I am going to try to get better at this for you. If you're given this fraction to work with, the 123/10,000ths, once again, you would write down 123 as your whole number, and you would place your decimal here, right? And then you count the number of zeros, 1, 2, 3, 4, and that's how many places you're going to move that decimal. 1, 2, 3, and 4. Hence, this is how we write the decimal 0.0123 or 0.0123/10,000ths, as you see written right here. Okay? All right, so for the last example, we have 1 7/8. Now, and let me erase this annotations because it does not move with us. All right, let's do that. Annotate, and we'll take the eraser. All right, let's erase that. And I thank you for your patience bearing with me through this video, because you know, we're all trying to learn in these weird times that we're in. So I thank you for that. But if you see here, okay, the first two, that was pretty simple. Their denominators were base 10, as you were expecting. But this one is not. This one has 1 7/8. So you might say, how do I write 7/8 as a decimal? Well, officially, you can see here, this is how we write 7/8 as a decimal. We read the fraction as what it is, which is a division problem, if you remember from our conversations in chapter 6. So this would be reading from top to bottom as 7 divided by 8. So that's exactly what we do. We do 7 divided by 8. Here's the problem. How 8 can't go into 7? 7 is smaller, right? So we add the decimal point that's always there, and we add a 0 for good measure. So that instead of going 8 into 7, 8 is now going into 70. But that decimal point that we added, we need to add into our answer as well. And since we're not going into the 7, we put a 0 there as a placeholder. And we're going into the 70. So we ask ourselves, how many times can 8 go into 70? Well, about 8 times. 8 times 8 is 64. We do the subtraction, leaves us a remainder of 6. Very important to note that now that we are, in essence, dividing a decimal, because that's what we've created now, right? We're not allowed to have remainders. But you know that we can add as many zeros as we need to the right of a decimal point because it doesn't change the value of the original number, right? So we can go ahead and add another 0, bring that down, and now that 6 automatically becomes a 60. And we can say to ourselves, how many times does 8 go into 60? Well, it does that 7 times. 7 times 8 is 56. We do the subtraction, we have a remainder 4, but we're using decimals in our division, so we're not allowed to have a remainder. We're going to go ahead and add another 0, bring it on down, and turn that 4 into a 40. And now we're going to say, all right, well, how many times can 8 go into 40? Well, that's easy, 5 times. 5 times 8 is 40. We go ahead and subtract. We no longer have a remainder. We are finished, and we have effectively converted 7/8 into its decimal counterpart of 8.875. Therefore, 1 whole and 7/8 could be written as 1.875 as a decimal point, and it would be read as 1 and, remember we always read the decimal point with the word and, 1 and 875 thousandths, because that 5 is in the thousandths place. Now you will note that I have put a very big highlighter here, that this is how we determine decimal value for any fraction. Please recall this because we're going to use it in a moment, okay? So now that we've discussed the different ways that we can talk about decimals, there's a theorem that you should be aware of that goes directly applicable to what you just saw me do with that 7/8 in the decimal 1 and 7/8 that we turned into decimal 1 and 875 thousandths, right? 75 thousandths. And this is the theorem that applies. In this theorem, it states that if we let the fraction a over b be a fraction that is already in simplest form, and then a over b will have a terminating decimal that it can be represented as, right? Terminating decimal means it does not go on forever, it does not repeat forever. As you saw with the 7/8, it did not go on forever, it did not repeat forever, it ended at 0.875, right? Now, this is only true if it follows the following parameters. Only if b, the denominator, contains only 2's and 5's in its prime factorization. If that is the case, then you will be able to have a terminating decimal that represents the same fractional value. If that is not the case, you can still turn it into a decimal, but it will be an infinite decimal, like in the case of pi, which is 3.14 going on forever and ever and ever, or in the case of 1/3. 3 is already prime, it does not have any 2's and 5's, so when you turn 1/3 into a decimal using the method that you just saw me use here with the 7/8, it repeats on and on and on and on and on as 0.33333 on into infinity. So only fractions whose denominator, the b, contain only 2's and 5's in its prime factorization will allow you to find a decimal version of that fraction that terminates. Otherwise, you'll always end up having to round off a little bit because you will have infinite decimals or non-terminating decimals. That is one of the reasons why people say that fractions is the exact form, because there are so many more fractions that are turn into infinite decimals than there are fractions that turn into terminating decimals. Okay, but so that you can see exactly what we're talking about, here's that 7/8 portion from that previous example, where 7 would be the A and 8 would be the B, right? And as you can see, according to the theorem, the 8 has to break down to a prime factorization that contains only 2's and 5's. And if we take the prime factorization of 8, we can break it down into 2 times 4, and we can take that 4 and break it down into 2 times 2. And as you can see, the prime factorization contains only 2's, which according to the definition means that it can be expanded to a power of 10. And sure enough, 8 can be. If we multiply 8 times 125, it turns into 1,000, which is a power of 10. So it does fulfill the requirements of the theorem, hence why 7/8 can be turned into the terminating decimal of 0.875. And you can see here that I'm recalling the previous example that you saw me break it down into just that terminating decimal. Again, should you have any questions on that, please feel free to reach out and let me know. All right, the last topic for today's lecture is ordering decimals. Like any other version of a number, we want to be able to put it into order from least to greatest, or to determine which one's greater, which one's lesser, and or whether or not they are equal. So it is important that we be able to order these decimals. And one of the ways that we can do so, there are 4 ways, and you can see here that terminating decimals, and we're limiting our conversation to just terminating decimals. We are not going to bring into our discussion for the time being non-terminating decimals, although we would still be able to use the same methodologies. It's just that it wouldn't be as comfortable because they go on forever. All right, we'd have to round them off to fit them into our conversation. So it's just better for us to focus on terminating decimals. Terminating decimals can be compared in one of 4 ways, and therefore using these ways, we can place them in order from least to greatest or greatest to least in either ascending or descending order. And that's what these arrows mean here, ascending or descending order. So for the purposes of using all 4 ways, we're going to compare the same 2 decimals to determine which one's greater, which one's lesser, okay? If we use the 100 square method that we spoke about earlier, you would take 100 square and you would shade it to represent 7/10. Since this is 7/10, I'm going to shade in 7 whole columns of my 100 square. And then for my decimal of 23 hundredths, I'm going to go ahead and shade in the 2/10 that I have there in the tenths place, and the 300ths that I have there in the hundredths place. And visually right away, I can tell that more area of the 100 square is being covered by the 7/10 than is being covered by the 23 hundredths. So clearly 7/10 is a larger decimal. Now, again, the 100 square method is not going to be that comfortable for decimals that aren't clearly in using the base 10 concept. But it is a nice way to visually represent and visually be able to analyze which of the decimals is larger. It's a good way to introduce it, particularly to children, because as you know, visual aids that help make things concrete are always useful when introducing it to students for the first time. Now, the number line is also useful. As you know, it's a tool we keep going back to using, and it's always useful when teaching numerical concepts. We can take a number line and divide it into 10 equal parts from 0 to 1, and then highlight 7/10 of those, 1, 2, 3, 4, 5, 6, and 7. And then highlight 23 hundredths of it, which would be 2/10 and then 3 little hundreds. So 23.23 would be somewhere right here. And immediately, again, visually, we can discern that 7/10 is clearly a larger decimal than 0.23. Okay, but when we're dealing with very large decimals, both of these first 2 visual methods are not comfortable to use. They become very cumbersome. So of course we have to have other ways that we can analyze which decimal is larger and which decimal is smaller. And so therefore we have the other last 2 options, which help us to do so a little more efficiently for decimals that would be too large to represent visually by using the 100 square or the number line. And we have fraction form as one of those useful methods. This is where you take your decimals and you turn them into their corresponding fraction form. Now, 7/10 is easily written as 7/10, and 23 hundredths we can easily write as 23 hundredths. Okay. Again, when teaching this to students, there is a way to do it, and I'm going to try to use that annotate again to see if it's helpful. Okay, and that would be where you take, once again, you take the numbers, the non-zero digits after the decimal point, and you write them as your numerator as if they were a whole number. Then you write your denominator to have a 1, and you add the number of zeros as you have numbers behind the decimal point. So I only have 1 number behind the decimal point, so I only add 1 0. Here, once again, I would move my decimal point all the way over to the right to convert it into a whole number. I write it as the whole number 23 for my numerator. I write a 1 as my denominator. I count how many places I moved my decimal twice, so I add 2 zeros, and that's how I turn it into a fraction. This is a useful way of teaching it if a person is yet not very comfortable going from 7/10 as a decimal to 7/10 as a fraction. Okay? Presumably you all will be, so I'm not requiring that you show me this level of work when you're converting from 7/10 decimal form to 7/10 fractional form. All right, I'm going to go ahead and try to erase that now. All right. And once you've turned them into fraction form, now you can compare them. But remember that when we're comparing fractions from our conversations in chapter 6, we have to compare them using common denominators. So we need to get a common denominator between 10 and 100. So for that, we always find the least common multiple. The least common multiple between 10 and 100 is 100. So we go ahead and find the equivalent fractions. 23 100ths stays 23 100ths. 7/10, when using the common denominator of 100, becomes 70 100ths. And now I can compare them just looking at the numerators, 70 and 23, and clearly 70 is larger than 23. So since 70 100ths is larger, its equivalent original fraction, 7/10, is larger. Therefore, its equivalent original decimal, 0.7, is larger than 0.23. Okay, so that's one way of comparing decimals using fraction form, which is more efficient than the visual representations of the hundred square and the number line when using larger decimals. Finally, this is the method that I find the most efficient, and that's simply to compare them using place value. To use place value, you simply line them up by lining up their decimals, and you go to the very first place value where both decimals have a different digit. Right here, I see that in the 10th place value, I have a 7 and a 2. They are different. It's the first place that's different because obviously the whole number place value is the same. They both have 0, right? And then you take just the place value where they were different from left to right, which was 7 and 2. So 7/10 and 2/10, I compared just them. 7 is larger than 2, therefore 0.7 is larger than 0.23. This I find is the most efficient method for comparing decimals, particularly ones that are not convenient to do so using the visual representations of the hundred square or the number line. Okay, now a couple of notes before we wrap it up. As we move on to section 7.2, we're going to discuss this note here in blue even further and in more detail, but it's good for you to note from now that the operations of addition, subtraction, multiplication, and division are performed very similarly using decimal numbers as we do with whole numbers. There are some slight adjustments that we make, which we'll have more of in the next section, but for all intents and purposes, what you can do with whole numbers, you can do with decimals as far as the operations that we use. Okay, and the next note, and this is just because it's a good thing to note for you, particularly when you're teaching mental math, which, as you will note, for those of you that have been doing observations and things in the classroom already, or you were doing into all this craziness, mental math is an important part of the mathematics that we teach here in New York State. And it is important to note that when you are multiplying decimals by 10, you're always moving the decimal point to the left by the same power of 10. So for example, if I take the decimal 0.3 and I multiply it by 10, which in essence is to the power of 1, then my decimal point will move to the left 1 place. Hence 0.3 times 10 becomes 3, where you can see the decimal point moved to the left. And I'll go ahead and use that annotation to assist us again. Okay, since I'm moving to multiplying by 10 to the power of 1, my decimal point moves 1 place, okay, to the right, turning it into 3. And this should say right. So let's cross that out and say right. There you go. Okay, so it moves 1 place to the right when you're multiplying by 10 because it was to the 1 power of 10. If this had been to 100, which would have been to the power of 2 tens, then we would have moved it over to 2 places to the right. And the same thing, the opposite is true, and I can see that that's an error here, so I'm going to go ahead and cross that out and write left. And sorry, I feel like I look like a toddler writing here. So when you're dividing decimals by 10, you move the decimal point to the left by the same power of 10. And again, in here in our example, you can see that this is 10 to the power of 1. So we're going to move our decimal point to the left once, and we move it over once, and there you see it. Now 0.3 divided by 10 becomes 0.03. The decimal point has moved over once to the left. Apologies again, like I said, I'm trying to improve these things, but as I'm sure you are under a lot of stress trying to figure out how to do all these online courses now, which is not what you signed up for. I'm trying to figure out how to do all this for you as well, and clearly having issues. But I'm glad that we were able to catch them together. Anyways, I hope these notes were helpful to you and this explanation was helpful to you. Please watch this video, go through these notes, and then you can do the homework. The homework that is being assigned for this section is on page 259 to 260. It's set A problems. It's problems numbers 1 through 17. And for any one of those problems that has multiple parts, only do parts A through C. Do not complete the rest of them. If they've got more than A through C, you don't have to do those parts. Just do parts A through C. It's only applicable, it's applicable to most of them. There are a couple of problems that do not have parts, but for most of those problems in problem set A 1 through 17, they have multiple parts. Only do parts A through C. Okay? All right, guys, I look forward to seeing you live on Friday. This is your Wednesday class, this video and the notes and the homework. So the homework will be due, making it due on Monday to give you a chance to turn it in, because we do have to do it via digital Dropbox, and I have to sit and grade your test tonight. So we'll make the homework due by Monday before class via digital Dropbox, okay? All right, guys, see you later.